lectures. Right, so today I'm gonna present you and discuss a bit the three methods that we saw at the end of last lecture, basically. So just to give and to make a quickly recap, so we started from cosmology. We looked at the polarizations derived in the quadruple approximation. We saw why actually it turns out that we have the luminosity distance in the waveforms and also redshifted masses, therefore. We saw that what are like the complications, if you want, of getting the L, given the degeneracy of this parameter with others in the amplitude of the waveform. And then I built on this, saying that basically we can constrain the L, the luminosity distance, and so this gives us like a new way of measuring distances at the cosmological scale, and therefore we can also probe the cosmological parameters using the luminosity distance redshift relation that we would like to fit. Now, this relation requires the definition of standard science. This relation requires also the redshift of the gravitational wave source. And so we discussed three methods, right? So the identification of an electromagnetic counterpart using spectral features in the gravitational wave source population. I will explain what this means. And then finally also using galaxy catalogs or galaxy surveys, if you want, to add additional information about the redshift. Again, these are all statistical methods, number 2 and number 3. Number 1, I mean, it's also a statistical method, but in some sense, like, it really relies on the observation of one electromagnetic counterpart. Then, of course, there are statistical uncertainties that you have to put inside the estimation of H0, but it's, yeah, I would say the analysis in principle is easier. Okay, so let me start then with the first method. So the first method is the identification of an electromagnetic counterpart, right? And so far we only had one event for which we had like confirmed EM detection, and this was GW17 or H17. So 17 was the first binary neutron star merger observed with LIGO-Virgo detectors. It's a 3-detector detection. So this is a very special event because basically here what I'm showing is like the projection of different sky localization obtained with different instruments. So starting with LIGO. So if you consider only the 2 LIGO detectors, which we're observing at that moment, we have something which is like more or less 190 square degrees in the sky. Then if you add Virgo, because Virgo was there, basically kind of 1 week or a few days after it joined the network in 2017, you get this smaller region here of roughly 30 square degrees. But the nice thing about this event is that actually it was followed also by EM counterpart. So by EM counterpart here I mean an electromagnetic signal which actually has been produced in different bands of the electromagnetic spectrum, starting from the GRB, gamma ray burst, short gamma ray burst, which has first been observed by Fermi, who triggered the source around this area, which is roughly, I think, 1,200 square degrees maybe. And then there was another, actually, GRB detector satellite who didn't trigger on time because it was kind of a sub-threshold, but then once Fermi said that actually there was something, also integral observations has been used, and basically by triangulation this allowed to further reduce like the area in the sky. And this helped also in the identification of the electromagnetic counterpart. So what I'm showing here in these other two plots, it's basically the observation in the optical. So the counterpart, which is shown here, this is what one of the telescopes observed like 10 hours, 11 hours after the merger, after the time of coalescence given by the GW event. And this is like how the same region in the sky looked 20 days before. And you see that there is the appearance of this point, this tangent, which is actually what near the galaxy NGC 4993, which is actually the BNS. Now, I could say several things about this event, but I won't because I don't really have much time. But basically, so from the observation of the GRB, the first thing you can do, for example, and that people did, was to constrain the speed of gravity, so the speed of gravitational waves. This is because from the distance to the source that we know from the GWs, for example, we have the arrival time of the GW. We also have the arrival time of the GRB, which was likely more or less 1.7 seconds after the merger. And then we can compare basically the time it took for these two signals to reach us, and somehow to get an estimate of the speed of gravitational waves, which, as you can see, if one does the analysis, turns out to be quite close to the value of the speed of light, right, at the order of 10 to the minus 15. This plot shows something that I think you may have already seen, probably also in some of the hand-on sessions maybe that you did. These are frequency time plots, which show basically how the GW signal evolves in time as a function, in frequency as a function of time. You can see that this was, at the time, I think, the loudest event observed in terms of SNR. I think it had something like 32, the network SNR. It was mainly observed in LIGO. You can see the track here, and in LIGO Hanford, sorry, and LIGO Livingston as well. Now, LIGO Livingston has a kind of it was not easy because there was actually a glitch. I think Stas showed actually one slide at the very end of his last lecture where there was like a huge, gigantic glitch that was kind of overimposing on the track of the signal. And so for this, work has been required in order to model that glitch and subtract it from the data. Once this has been done, then data from Livingston could also be used. Just a comment about Virgo. So you don't see anything here, right? The SNR here, I think, was something like 2. But there is actually a reason. And in fact, the fact that we didn't observe basically nothing here was very helpful. And this is because at the time of the observation of this event, all of these 3 detectors, in principle, could have detected this source. They were online. Also, I think the BNS range, so the number that we typically give to assess like how far away we can detect a BNS, was something like 50 megaparsec. And this source was like at 40 megaparsec, right? While these were like, I guess the sensitivity of these were around 100, I think, megaparsec. So in principle, we should have seen it, right? But we didn't see it because actually detectors have some sensitivity. I know, we know that basically they are kind of 4 pi detectors, no, GW detectors, but there are some regions actually which are called kind of blind spots where basically they are not sensitive. And it turns out that indeed the source, BNS 1717, was in one of these. So this actually helped even to give more information about the sky localization, because it means that we didn't see it actually because it was in one of these blind spots. Right, so after this, follow-up. So as I said before, we had first like the gamma ray burst. Then, so at the time of the observation of the trigger, actually, it was, so the localization here is like in the southern hemisphere. So you need a telescope in the southern, hemisphere to observe it. But at that time, it was like something like 9, 10 in the morning. So we couldn't directly point to the source. So we had to wait like 10 hours. And after 10 hours, then everyone basically started pointing at the sky region of the source. And I mean, here there is a list of all of the, you can't read it, but there is a list of all of the telescopes that basically made their observations in the optics about the M counterpart. After the M counterpart, which, by the way, was also followed by UV and infrared, we observed X-ray emission. And then, finally, actually, first I think we observed, it was first the X-ray, and then finally also the radio emission. So, many different observations. These are all of the, for example, I think these are all of the, some of the optical observations made by several telescopes. Most of them are in Chile. And then we also have like the observation in radio and in X. So all of this to say that this was an incredibly interesting event. And this allowed us also, once we were confident that the M counterpart was associated to this event, and that we knew actually the redshift of the galaxy, of the host galaxy, this allowed us to make the first measurement of H0 using gravitational waves. And this has been presented in a Nature paper in 2017 by the LIGO-Virgo collaboration, plus the different other collaborations that helped in getting the redshift. So this event was at 40 megaparsecs, so it was very close by. And this means that we can just basically use the Hubble law if you want, because all of the other parameters are not accessible at this very low redshift. And what we basically obtained was so a posterior distribution for the Hubble constant. Right? You have the probability versus the values of H0 here. Some things that I want to stress here. So first of all, I think that in principle, this curve here could have peaked anywhere in between this range. So I think it's remarkable that with just one event, we see something that is in the region where other electromagnetic observations are pointing us about the value of H0. Secondly, you can see the shape of this posterior, no? And for example, you can see that there is a large tail here on very high values of H0. Why? Well, because this is due to the degeneracy of the luminosity distance with the inclination angle of the source. You can see this, for example, in this plot. This is another plot shown in the Nature paper, where you have, this is a two-dimensional plot, right? So you have the probability that is coming out of the screen here, and you have cos iota. Iota, again, is the angle of inclination between the line of sight and the normal to the binary plane, and H0. And you see that there is a large degeneracy here. This degeneracy reflects, in fact, the degeneracy that you have between the luminosity distance and iota. So as I think I said also last time, there is this degeneracy, right? Which you can also see even with the simplest waveform that we looked at in the amplitude. And this is because, basically, as I was saying, I can have like a close-by source, so with smaller DL, which is edge-on, or I could have a very far away source, which is phase-on or phase-off. And this is basically what you can see here, right? Because these are just, this is just the angle, right, theta. And indeed, this event was kind of more probably towards the phase-off configuration. But you see that as long as this is the case, indeed, it means that the source could have been like more distant. These are like, okay, just look at basically the blue curve, which are just the analysis obtained with the gravitational wave data. You could also kind of put inside the prior of your analysis the fact that we knew the electromagnetic distance, that we knew the distance from the electromagnetic galaxy, from the electromagnetic observation of the galaxy to improve this. But just look, at the blue curve here. So this degeneracy reflects also in the H0 posterior, because basically, H0 is just linked to the luminosity distance by this simple relation. And so this is the reason why you have a long tail here on high values of H0. Now, this is super cool. The problem is that I mean, with just one source, we cannot really have a very precise measurement of H0. So here we are probably on the order of maybe 15% or 20, 15 probably. So it's not comparable yet, not yet, to supernovae and the CMB, which are on the order of 1 or sub% level precision. Okay, so this is, again, I will not talk much about bright science because, I mean, this is just the only event we had so far. So I will now move to the other two methods, and we'll tell you how we do the analysis when we don't have an electromagnetic counterpart. Second method. So the second method, I said we want to use spectral features in the mass spectrum. What does it mean? So as we saw, we have basically the quantity that we measure, which is a detector frame mass. No? This is like the redshifted value of the mass that we measure because of the cosmic expansion. And so from this relation, you can see that this is what the quantity we measure. The actual value of the mass of the black hole is actually another value, right? Which is the one you can see here on the right-hand side of the equation. And this is connected to the detector frame value by a 1 plus z factor. And now the redshift is actually linked to the luminosity distance and to cosmological parameters. No? So one can, for example, invert this relation, the luminosity distance redshift relation, and get the redshift as a function of the luminosity distance and the cosmological parameters. But this basically tells you that there is a connection, no, between, again, the usual suspects, so the luminosity distance, the redshift, and the cosmological parameters. Now, if one had some knowledge about the source frame value of the mass, then we could kind of, infer the redshift, which is eventually what we want to get. Now, the point is that at a single event level, we cannot really break this degeneracy. But if we consider like an ensemble of events, and we look at the distribution of the values of the component masses, then if there is like a shape in the spectrum, which could be, for example, like, I don't know, a peak, or maybe an abrupt end at some values of the distribution, then those values, in the end, that distribution should also be shifted, because we are looking at the detector frame values of the mass, not at the source frame. So in other words, there would be a difference between the source frame distribution and the detector frame distribution, which is kind of shifted. So what we do here is to look for, I say, landmarks in the mass distribution, and we want to see how far they appear kind of shifted. So here I'm showing you like, this is a sketch, okay? This is not like a real distribution. But imagine that, for example, the distribution of the masses, the first primary mass, where M1 here is defined as the more massive among M1 and M2, has some kind of cusp, okay? Imagine that for some reason, I don't know, nature decided that black holes have this distribution. Now, this is how it would look like in source frame detector, right? It has a peak at 40 solar masses. But actually, we don't observe this. What you observe is this, right? A distribution which is actually shifted, and whose peak is actually at 50 solar masses. And so if we knew actually that the source frame value had to be at lower values, we could then say, okay, well, by measuring how much the value has shifted, I can get the redshift. And this is like the basic idea behind the spectral Sudden method. So by measuring how far away these peaks or features kind of shift, we can obtain information about the redshift. An example. So this comes from the latest gravitational wave cosmology study that we did, in which I was involved, in the LIGO-Virgo-Kagra collaboration. So these are like, for example, the 3 models that we considered in our analysis. These are source frame mass distributions, okay? So we need to model the source frame mass distribution. And for example, if we only want to look at black holes, which is basically what has been done so far before this paper, we have several phenomenological models for these mass distributions. For example, a typical choice was like a power law plus peak, like, again, this is like the probability of M1, given some hyperpopulation parameters. I will define those later, as a function of M1. And for example, first observations until, I think, GWC2 probably, even GWC3, I think, were showing that if you just take, you know, the histogram of the you know, the detector frame masses, you were getting something which was like this. You have like a power law, and then there is a peak at some point, a Gaussian peak, which is modeled as a Gaussian peak. And this is one possible distribution. Another possibility is that maybe there is like a second peak, or if you want an additional peak at lower values of masses. And this is another model, which we call multi-peak. And now we also introduce another model, which allows us to basically account for all of the sources, including also neutron stars and black holes, which has a more complicated functional form, but which is basically able to account also for the neutron star masses. Go ahead. Yes.
Sorry, maybe a question, but so all of this is supposed to be source frame, right? But all
Yes.
we have access to is detector frame. So how do you know that, like, it's a bit of a,
well,
you know, yeah.
As I was saying before, so like what we measure, in principle, will be something which is kind of shifted, right, as compared to the values that we could expect to be in source frame.
But how do we know? How do we get these plots? I guess that's my question. Because this you cannot use the detectors, because otherwise you're also influenced by the, like.
Yeah, I mean, you can look at the detector frame distribution, and what we expect is that there should be some kind of shift. We don't know the absolute values of these peaks. This is actually the values of the peaks, for example, and even, I don't know, M max, M min, the power law index, and so on. These are parameters we infer.
So I guess that's my question is, what does phenomodels mean here? Is it like we saw yesterday?
Yes,
like this?
phenomenological here means like, again, based on the observations, based on, for example, the detector frame mass samples that we get from the parameter estimation of the gravitational wave events. Those are detector frame masses, but in the end, we use them to infer the source frame masses. So if you want, one could say we have a look at the distributions based on the quantities that we observe in the detector frame, and then based on that, we can kind of try different models, which could have some actually astrophysical motivations behind. For example, there could be some cutoff at higher values of masses because of some astrophysical mechanisms coming from motivated by stellar evolution theory, or you could have, for example, peaks which may be described by multiple peaks which may be representative of different formation channels of the binaries. So in principle, one can try different models, right? Here I'm just showing when I say phenomenological, I simply mean that if we look at the population analysis of these events, which are also presented in a companion paper by the Laghi collaboration, you can try different models, and again, based on the observations and on astrophysical assumptions, you can choose some of these and then test them.
Thank you.
There.
I guess that the distribution that you observe in the detector frame informs you also in about which one of the models, the phenomenological models, is more correct. So do you take that into account when you do this analysis, that there are models that resemble more what you observe and others that maybe don't?
If you want, yes, because, for example, we looked also at the Bayes factors. So again, the Bayes factor is basically the quantity that tells you, based on the data, which model is preferred. Like Bayes factor between, say, for example, the multi-peak model versus the power law plus peak model would tell me which model is preferred among the two. And so there the data are basically telling me which model should I be more confident. So yes, I would say. Does it answer? Okay.
Sorry, I'm so confused.
Yeah.
So, but for the phenomenological models, you
Yeah.
don't use any inference from gravitational waves, right? Because in order to get the source frame from the detector frame, you have to assume a cosmology, no? That's what I'm a bit confused.
Yes.
So, are you
So,
yeah.
okay, if you want maybe from, instead of saying phenomenological, I could say astrophysical, even though, I mean, again, then the exact like interpretation of these shapes should depend on, you know, as I was saying before, maybe on stellar evolution theory or other things. Here I'm simply saying that, you know, I'm looking at the distribution of the mass values in the detector frame. They may have some shape. I just take, you know, a parametric form that is kind of similar to, you know, to the distribution that I see. And then I use that, I assume that that is similar or could model the source frame distribution. But I don't, you know, I don't fix the values of this distribution, right? I'm simply saying, you know, the shape should be this, but I don't know what are the values of the peak, of the sigma, of M min, M max, of alpha, of, I don't know, like the smoothing factor here. So these are all parameters that I'm sampling over. So it's just, you know, to have a guide, at least, to choose a functional form, right? Instead of choosing, I don't know, a straight line wouldn't probably fit like the distribution that I'm observing. How do you know that it doesn't fit back? I mean, if you look again at the distribution of the source frame masses, what I'm expecting is really just a shift of the characteristics of the distribution. And then, of course, I can have like confirmation from data about the Bayes factor, because if I see that basically using one model I get a Bayes factor of 2,000 against another model, the data also tells me that. Yes.
Just a quick question. So you expect a shift? Do you also expect a spread? I remember seeing, you know, graphs.
In principle, yes.
Fatty area.
Yeah.
Okay.
Yes. Okay. I don't know if we will arrive at Lisa, but okay. So this is like what is this? Yes, this is an example. This is an example of what we actually did with the latest GWTC4 catalog. And here I'm showing a corner plot. You have seen corner plots. But again, maybe, you know, at the cost of being a kind of pedantic, you have two-dimensional distributions here, right? You have different parameters. You have 4 parameters, H naught, mu G low, mu G high, and gamma. I will tell you what these parameters are. Basically, okay, H naught is the upper cost. Then you have mu G low and mu G high are the positions of the first and the second peaks in the primary mass distribution. So this analysis has been obtained assuming the full population, full POP 4.0 model, which is this. And here you have, for example, 2 peaks. And these are the values that we are inferring. Those mu refer to the mean of each of these Gaussians here. We are also measuring the width, by the way. So the power law plus peak model in total has, I think, 8 parameters that we are sampling on top of H naught. The multi-peak has 11 plus H naught. And full POP 4.0 has 19 parameters plus H naught. So in total, it's not easy, in general, to sample these parameter space because you have a lot of parameters, right? But anyway, so here I'm showing a subset of the posteriors that we actually have. Imagine that here you have a corner plot of 20 parameters, okay? Here I'm only showing the ones which are more interesting. What does it mean more interesting? It means the ones which show correlations with H naught, because this helps us also to understand why we get a value of H naught instead of some other. Gamma is the low redshift power law slope of the Maddow-Dickinson merger rate. This is another ingredient that goes into the analysis, as I will show you soon. But basically, again, this is just to show you that in principle you can have, and you can get actually a measurement of H0 in combination with all of the other parameters. This has been obtained like with two pipelines, the two that we used in the latest LVK cosmology paper, which are called GW Cosmo and Icaro GW, and you can see that they are pretty well in agreement. I can come back to the correlations maybe later, why they have this shape, and gamma as well. So, question?
Yeah. No? And if you choose another model, does it influence, like let's say you choose a single peak model, does it influence a lot your H0 measurement? Did you try this? It does?
Yes. Unfortunately, yes. And I will tell you why and also how. But not now. I guess in 3 slides maybe. OK. Now let me move to the third method. This is just an overview, then I will come back to the details of the likelihood that we use. Adding redshift information coming from potential host galaxies. So this is sometimes called, at least in the paper, in the latest LVK paper, we define it as dark-sided method. Sometimes it's also called the catalog, galaxy catalog method, galaxy statistical method. But I mean, this is just to make a clear distinction between spectral, where we don't use EM information at all, and dark, where we use actually galaxy surveys. So the idea here is that we want to use information from a galaxy catalog. So the event that you see here is called the GW190814. This was also a 3-detector detection. It is still like I think the best localized event that we have so far. This is like 20 square degrees if you take these two regions. These are just to tell you what you are looking at here. So these are like Bayes star. So Bayes star is an algorithm that is used to get low latency estimation of the sky localization of the event. It's a pipeline that you can also use. Using only LIGO and Virgo data in blue, in light blue. And as soon as you add also Hanford, you see the incredible improvement in the sky localization. OK, there are some degeneracies, but this is like, OK, I mean, this can be expected. What else? Combined PHM here means, I think, it's just the analysis that you do, not low latency, but after you have the proper parameter estimation. And it improves and refines the low latency one. So the idea here is that I have this super cool localization in the sky of this event. And then I want to look at the galaxies which could be in this sky region. And this is what I'm showing on the right plot here, where you have right ascension, declination versus right ascension. Each cross here is a galaxy. These galaxies are in a galaxy catalog compilation called the GLID Plus. And so for each of these galaxies, you see we are only taking those which are compatible with the sky location of the GW source. We have a redshift measurement. And indeed, what we are going to do is to take all of these redshifts and to use them to basically infer the most probable redshift of the source. We don't know exactly which galaxy could be the most probable, but actually in the end, we end up inferring this value, if you want. And this is the basic idea. I just want to mention that, OK, so references. Schutz, Nature 1996 was like the first paper that basically put out the idea. Del Pozzo PRD 2012, I think, is probably the first Bayesian analysis that took this idea and put it into simulations with LIGO, Virgo, probably Cagra detectors. But in any case, it was the first Bayesian, to my knowledge, I may be wrong, analysis of this method. Gray et al. 2020 is like a very a mock data challenge that some people in the LVC, like with collaboration, did to assess the method. Basically, it was like one of the first mock data challenges done using BNS simulations and computed with Bayesian parameter estimation. So it was kind of an important study. People outside the collaboration, when I say collaboration, sorry, this is like my bias, I mean always LIGO, Virgo, Cagra collaboration. For example, Fink et al., this is a group from Geneva that made I would say an impressive work. This paper is something like 80, 90 pages, but it goes through the details of the method as well, so I think it's a very nice reading. Palmese et al., this is another analysis that this group, US-based, they did several analysis using other catalogs outside of GLADE+. For example, they use, I think they've been using DESI, DS as well. Mastro Giovanni et al., 2023. I was also involved in this paper. Here we showed the method that I'm going to present you now, but basically which also goes into the details of this analysis. Gray et al. Is another improvement, and basically these two methods, the methods presented in these two papers, have been adopted now in the latest cosmology paper. And then there is, of course, okay, the GWC4 cosmology paper. So the idea is that by combining the information from many GW events, the contributions from the true host galaxies will grow, since they will all share the same H0. Right? So in principle, there has to be a true H0, if you want, that we want to infer, and this has to be common to all of the events. And so, like contributions from the other values of H0 will statistically average out, leading to a constraint on the cosmological parameter, in this case H0. And this plot comes from the latest, again, cosmology paper. We have the probability of H0 as a function of H0. And these are the different analyses that we did. You can see the spectral sign analysis, the one in my point 2 that I showed you before, which is given by the orange curve. You have the dark siren analysis, where on top of the spectral siren, actually, you are adding information from the galaxy catalog, and this is like method number 3 that I'm showing here. And then you have the dark plus bright sirens measurement, which is the final measurement that we give. Here we are adding information from the bright siren, which is just one, which is 17 at 17, yellow curve, to get the the black curve. Okay, this is like the final posterior that we have, and this is the latest measurement that we presented.
Why don't you add also the spectral sirens? Is there a reason? Sorry? Why don't you also add the spectral sirens in the black?
Yeah,
is there a reason?
Yeah. So the dark siren here actually means, this is defined in the paper, means spectral plus galaxy information. So dark here refers to spectral plus galaxy. The point is that what we showed in these two studies here, 1 and 2, is that in the end, even if you just want to use galaxy redshift information, you always have also to infer the population parameters. So in other words, what I'm saying is that the dark siren analysis is always the spectral siren, so you have to do the spectral siren analysis and choose a population model, plus galaxy redshift information. So whenever I say dark, keep in mind that I'm referring to spectral plus galaxies. So this is like adding on top of the information that we get from the spectral siren, which, as you can see, gives you the main bulk of information. You get also additional information about the redshift, and you get something different. And an improvement compared to the spectral siren, looking at the dark siren posterior, is of roughly, I think, 9%, more or less, at the moment. There are several limitations, and I will tell you why.
I have two questions. So first, why is the black one broader than the yellow one? So you include information from two sources, and it is broader, at the peak than...
I would say it is broader simply because it is broader like... toward higher values as compared to the bright siren. So you are basically you are kind of combining the yellow curve with the blue one, which is larger. It has a larger tail, so in the end it will broaden the measurement from the single bright siren. It's not like adding the two posteriors would give you something which will necessarily shrink.
Mm-hmm. And the second question is, if you look at the prediction of how the number of observations are growing, mm-hmm. and extend it to the future, how much time do you have to wait if you don't have any bright sirens that you can resolve this discrepancy between the Planck and?
Yeah. So
approximately, 100
approximately
years, 1,000 years.
Because there are many factors which go into the analysis that can actually change your predictions. I would say probably imagine an O5 scenario where we have, I'm thinking about a recent study, for example, Borghi et al., 2024, where they made this analysis assuming an O5 network, so LIGO Virgo, Kagra, LIGO India. And they looked at, I think, the 100 loudest events, or at least events with SNR greater than 25, if I'm not wrong. And I did this analysis with a galaxy catalog, assuming that the galaxy catalog is complete, so that it doesn't suffer from any incompleteness, which is also another important point. And they considered two scenarios, one where the redshift measurements from the galaxies were photometric, and a second scenario where they were spectroscopic. Now, the difference between these two is that spectroscopic measurements are actually quite more precise, okay, on order of magnitude, I don't know, but yeah, a factor probably 10 or 100 potentially from other photometric measurements. And so if you have better measurements of the redshifts of the galaxies, this naturally gives you more information about the full analysis. And their point was that we would need probably, I think, a spectroscopic galaxy catalog, 100% complete, with 100 dark sirens to get something on the order of 1%. If you have a photometric galaxy catalog, then this boils down to, I think, using the same 100 best GW events, something like 9-10%. So you see that there is some uncertainty. I would say maybe with the 100 best events in an O5 setting, maybe we could have something on the order of at the level of shoes. But again, we cannot really because there are many things that might change. For example, I gave you the example of photometric versus spectroscopic, but other things. Also, it also depends on the sky localization of the event. So if we have something which is more or less well localized, so this is the number maybe I could give you. But okay, so now a little bit more technical part here. So how do we do this analysis? I mean, I've been showing you here plots and things, but actually, how do we do this? So to do this, we need to work in a Bayesian framework or a hierarchical Bayesian framework. I want to give you two references here. So the first one is Mandel, Ger, Farr, 2019. This is the usual reference which is given to basically introduce the hierarchical framework method in case of selection effects. It's a quite short paper. Maybe it's not super easy to read if you are not very familiar with in general, with this kind of analysis. I would instead maybe suggest the reading of this. Salvatore Vitale, not Stefano, Salvatore Vitale et al. This is chapter 42 in the Handbook of Gravitational Wave Astronomy. This is a very short book. It's only 1,900 pages. You can have a look, however, only it's a handbook, right? So it has to contain 1,900 pages. You can have a look only at chapter 42, okay? Or, if you don't want to have a look at this gigantic book, you just take the archive version. This is very nice, I think, because it goes through the step-by-step derivation of the likelihood that I'm going to show you now here, which I won't have time to go through because, so, for the spectral and dark-sided methods, what we say is that the GW sample that I have, for example, I observed 50 GW sources, actually 140, say, is modeled as an inhomogeneous Poisson process, which is constant in rate, in detector frame time, in the presence of selection effects, because the selection effect here means that our detectors have a finite sensitivity. And so there will be some sources which will be easier to detect and others which will be harder. And we have to account for this, because otherwise, if you are inferring population properties, we might get biases. And this is similar to, if you want, to the Malmquist bias that affects like EM observations. Inhomogeneous, what does it mean, inhomogeneous? So inhomogeneous means that the rate of events, imagine like a Poisson model, is not constant in the parameter space. There will be sources which will be easier to detect, again, because maybe of the parameters of the GW, and sources which will be less easy to detect. So in this sense, we use the word inhomogeneous here. The parameters we want to sample here are cosmological and population parameters. Here I'm calling them lambda C and lambda P. Lambda C might include H naught, for example. Lambda P will include the parameters of my mass distribution, for example. So if I have, say, again, say the multi-peak model, I will have 11 parameters which describe the parametric form and shape of the distribution, and those 11 parameters will be this lambda P. And these are called hyperparameters. Why hyper? Well, because, again, this is to emphasize that these parameters do not enter directly in the waveform of the gravitational wave. Those are not really the parameters that I'm getting from the parameter estimation of the GW sources. A GW waveform may have, I don't know, say 9, 11, 13 parameters. I sample those parameters, and then I use those parameters to infer another level, if you want, of parameter space, which is these hyperparameters. And what do we do here? I mean, this is Bayes' theorem, no? P of lambda, the probability of getting these parameters given a set of events, x. This is my data, okay? And this is proportional to an hyperprior, P of lambda, times a likelihood, which in our case is called hierarchical likelihood, if you want. I mean, I would simply refer to it as likelihood. And so, as I was saying, lambda here it will be a combination of these two. This is like the hyperprior, and this is the hierarchical likelihood, which should describe the observations as a function of the hyperparameters. Right? This is just Bayes' theorem, no? I'm not showing like the evidence, but okay. So, how does this likelihood show? So you can derive this expression. Okay, here I will just tell you what these terms are, basically. In general, this is like an ST integral, because as I told you before, we have something like 14 or 20 parameters we need to sample at the same time. So it's not easy. Of course, we compute this numerically. But basically, you have the likelihood here proportional to a product over all of the GW events that we have. And then you have like, a factor which represents basically the observation time measured in the detector frame. If I observe for, I don't know, like 2 years, there I will put this number there. And then here we are integrating over each of these integrals, right? There is a product here. Over the GW likelihood, this is like the likelihood representing the gravitational wave single event parameter estimation. And so it depends only on the parameters of the source. For simplicity here, I'm not putting vector signs, but this theta here represents basically all of the parameters which enter my waveform. Again, 9, 11, 13, whatever, depending on the waveform model that you choose, for the event I. I here refers to the event. So this is like the GW likelihood. And then on top of that, again, since this is kind of Poisson process, I have an event rate. An event rate which is written, which I can write as the number of CBC sources, compact binary coalescence event rate in source frame time per parameter, if you want, per parameter space d theta I. And then there is also a factor 1 over 1 plus z, which simply comes from the fact that we are converting this distribution from detector frame to source frame. In general, I would write this as dn CBC over d theta I dt detector, but I can write this as dn CBC over d theta I dt source frame times dts over dt detector. And this dt source over dt detector is exactly this. Again, this is something we saw like the first lecture. And so this is like the structure of the likelihood. Now, there is another piece of another ingredient here, which is this e to the minus an exp. An exp here is the expected number of sources. Yes, go ahead.
Does the likelihood encode also the selection effect?
This is exactly what I'm going to tell you.
Okay,
now.
sorry.
Yes, it must, because basically it gives you, this NXP is like the probability, sorry, no, NXP is the number of expected, not experimental, the number of expected sources that I am, that I expect to detect given a number, given a set of hyperparameters. And this depends on, you have another expression here, which is basically similar to the integral that you have here. But there is another factor here, which is p det, the probability of detection of a source of parameters theta, again, this is like a vector, for a given value of lambda. For example, for a given value of h naught, or for a given value of all of my hyper population parameters. And this clearly has some dependence, right? Because, for example, if I change h naught, I'm going to shift, if you want, the luminosity distance, because those are connected quantities, right? And so it will depend on, and if I have, a close by or a farther away source, then the probability of detecting it will change. So this factor here basically accounts for the selection effects, for the GW selection effects. And so now the question is, this term here is basically the one that we need to model. But how do we choose this parametric form? And now here we make a distinction between the spectral. I make a distinction between spectral and dark siren analysis. Let me start with the spectral one. So the compact binary coalescence merger rate, is parameterized in terms of redshift and source frame time. So for example, here imagine that, again, I'm abusing the notation here, but imagine that I am kind of separating the theta into the different parameters which are included in it. So for example, we have the masses. Again, this is abuse of notation. Here I'm simply referring to M as the two masses, M1 and M2. I need to distinguish this because later on I will introduce the apparent magnitude, which is another thing. Then we have basically the NCBC, so the number of CBC sources as a function of per mass, actually, per M1 and M2 mass, plus other parameters, the theta. For example, one may include the spins, but we will not consider them here. Per sky position, per redshift, per time. So one choice that is usually done here is to model this rate in terms of some functions. We have first a function which I call psi, MD. MD here stands for Maddow-Dickinson distribution. This is like the merger rate as a function of z. So it's basically a function that that goes like which goes like this. It's not symmetric, okay? Probably I drew it not super correctly. But it depends on 3 parameters. So like there is ZP, and then there is gamma, and there is kappa. So it's like a distribution of the rate of events as a function of Z. Typically, the assumption we make here is that the CBC merger rate follows the star formation rate. And this is the reason why we choose the Maddow-Dickinson parametrization. So this will give us, lambda p here represents, again, the population hyperparameters. And here in this case, we have 3 parameters that we will sample over, which are gamma, the low redshift power law index, and the high redshift power law index, kappa, and ZP, which is the value at which this distribution should kind of peak, again, because of stellar formation.
Are these only for stellar mass black holes?
Sorry?
Once again, are these only for stellar mass black holes? Because we see for LISA the merger rate is like orders of magnitude.
Yes. So are you asking about LISA?
For this, these are stellar for only for stellar. Stellar
I mean, in general, no. We used it, for example, also for the for neutron star black hole binaries, or even for neutron stars. So in general, I would say not only for stellar mass black hole, you cannot use it probably for massive black hole binaries or the black holes, because they won't follow this.
Okay.
No. You have another factor here, which is a comoving volume factor. This is simply telling you that we assume that the sources are kind of distributed, homogeneously and isotropically in redshift as well as in sky position. And finally, we have this P-pop. P-pop is the population model, the mass distribution, what I was showing you before. This is a probability density function which describes the distribution of the GW sources in the masses M1 and M2, which I'm not showing here, plus potentially other GW parameters. For example, one may want to include also the spin distribution of these sources. This is something that someone has been doing also. And so you see the main ingredients here are the merger rate, this which actually the DVDZ factor, which gives us a dependence also on the cosmology, because this is like a function of that goes like 1 over h naught cubed times an integral from 0 to z of 1 over e of z, where e of z is like the Hubble function, which is basically the equation I showed you before last time, I think, which is just the square root of omega matter, a combination of omega matter and omega lambda, times 1 over e of z. And then, so the main ingredient actually is P-pop. So it's how we choose this model, right? And this gives us information about the masses. Again, this is like the source frame mass distribution. What I'm inferring here are the population parameters of the source frame distribution, because the detector frame I already kind of, I could fit it. So what is the main limitation of this method? Well, if I choose a mass model which is not good, which doesn't describe correctly the mass distribution of my observed events, H0 can get actually quite different values. So here I'm showing you, this is again another plot taken from the latest cosmology paper, the probability distribution of H0 for different choices of mass models. This is one of the plots that we showed, indeed, to show how actually our measurement of H0 depends on the mass model that we use in our analysis. And you can see 3 posteriors here. PRP stands for power law plus peak. MLTP stands for multi-peak. And full pop 4.0 is just the full population, the multi-population model, which allowed us also to use events with potentially neutron stars. And you see, for example, that the multi-peak and the full pop 4.0 distributions of H0 are in agreement. At least they have their major mode in the same H0 value region. While on the other hand, the PLP model is giving you a quite higher values of H0 as compared to the others. And so there are basically 2 reasons for this. So the first one is that the power law plus peak model, we know that now based on population analysis, is not really able to describe the full complexity of the mass distribution. And the second one is why actually we are getting higher values of H0. So the reason is that in the power law plus peak model, which is again this model here, this model tends to put a lot of events at lower values of M. And now, if you remember that the detector frame mass is equal to 1 plus z times the source frame mass, lower values of the source frame mass means that basically I'm putting them at, since the detector frame mass is fixed, lower source frame values of the mass tells me that the redshift should be actually higher. And if the redshift is higher, then, just thinking about the Hubble law, I should have higher values of H0, no? Because dl is equal to c times z over H0. And since dl is fixed, again, by observations, I have a higher value, of z, and so I must have also higher values of H0. And so this explains why we have this kind of larger value here. On the other hand, the other models, which better fit the mass distribution of the events that we have observed so far, they give values which are more in agreement between themselves, and which are also, where one would expect actually to have the value of H0. So one has to be careful. One, in general, with this kind of analysis, we looked at the Bayes factors in this case for these events. We could only compare the Bayes factors of the multi-peak versus the PLP model. The reason is that for these two models, we are using the same data set, only black holes. In this case, we are adding other data, which are the events which could also include a neutron star. And so we cannot really compare, the multi-peak model with the full pop P because the data sets are different. Okay? By definition, the Bayes factors must have the same data set. No? It's the ratio of the probability of M1 given D over M2 given D. D data is the same. I cannot compare these two, or this with this. But looking at the Bayes factors of multi-peak and power law plus peak, for example, we found only a mild preference for the multi-peak model. But again, then with Bayes factors, there are also the prior choice that you put into your analysis, which might influence those values. For example, we also repeated an analysis where we assumed the same priors for the values of the peaks in these distributions, in this and in these peaks. So what I mean by peak, so it's again mu g basically, the position of the peaks and also the sigmas. We use the same priors in these two models, and in that case, for example, we found a strong preference for the multi-peak model over the power law plus peak. But again, this is kind of prior dependent, so we cannot really use it like to say that the multi-peak is better than the PLP. But in any case, so the full pop model is actually the one that we chose to present our results because it allows us to use more events. Because with this model, we can also include events which could have a neutron star. And this adds actually additional information. We might have also a dip here in between the range of masses between the neutron star and the black holes. This is something that, again, one expects, ideally. And so it has more features, and therefore it is more informative in the end. Now I will move to the third method, the dark-sided analysis. So this is more complex. And so what we have to do here is to add information also from the galaxy catalog, right? The likelihood in this case, at least the rate, the way in which we can model it, now depends on additional things. So we still have like the same ingredients as before, and this is the reason why I was telling you that actually the dark-sided method is built on top of the spectral sided method, because here we still have a p-pop, you see? But now we are adding additional information from the galaxy catalog, and this is encoded in two terms that you have here in the likelihood. So there is a first term that we call in-catalog term, and this term accounts for the galaxies which are in your galaxy catalog. okay? And then we have another term, which we call out-of-catalog term. And this out-of-catalog term basically accounts for the incompleteness of your galaxy catalog. Imagine that I am doing a galaxy survey with a telescope, and this telescope will be flux limited. So I will be missing some galaxies. And if I don't account for this, again, it's a kind of Malmquist bias, so I might get a bias in the measurement of H0. So these two terms are needed, in principle, whenever one is using a galaxy catalog which is not complete. And so let me try and explain a bit these two terms here. So first of all, just a reminder that we have, by capital M here, I mean the absolute magnitude, right? There is the apparent absolute magnitude relation that I'm giving you here. There is another complication, which is actually the fact that whenever we are using photometric galaxy surveys, we have photometric redshifts, and for those we need to apply K-corrections. K-corrections, I will not go into details of this, but basically are corrections that one has to apply in order to account for the potential evolution in redshift of the measurement of your redshifts. And these also have some kind of limitations in the range of redshifts that you can use. Right, this is just the relation between absolute luminosity and absolute magnitudes, given some reference values. And so, basically, starting with the in-catalog term, so you have that omega here is like the pixel area. What we have to do is imagine that I have an event, a sky localization, say, I don't know, here. I need to pixelate this sky region. And for example, we use HealPix, you use the usual tools that are used in this case. And in each pixel, then, you are going to compute this term here, which is, in principle, yeah, if you want, yeah, this term here, which is a sum over the number of galaxies in a given sky direction. Again, omega here refers to just one pixel. Imagine that I have many different pixels, and in each of these pixels, I'm looking and counting all of the galaxies. Then you have, this is a weight. I will comment about this soon. But this is the main term, which models actually the galaxy redshift uncertainty. Okay, this is the probability of Z. Z is the redshift of the source, which is the quantity over which we are marginalizing, right? This term is inside this integral in the end. And this is the probability of the source redshift, given that I have a galaxy redshift Zj with uncertainty sigma z. And these are typically modeled as Gaussians at the moment, what you are doing. So you say that basically your galaxy redshift measurement can be modeled as a Gaussian with some uncertainty sigma. For each galaxy, I will have this term. Then each term, each galaxy, can actually be weighted by, for example, the luminosity of the galaxy. And this is another choice that we usually do, and that we also did in the cosmology paper. For example, if epsilon here is equal to 0, this term goes to 1, and you are basically assigning equal weights to all of the galaxies, which are in my line of sight redshift prior. I'm basically saying that I don't know which galaxy was actually most probable, so I'm just assigning equal probability. Or if I choose epsilon 1, for example, then I'm saying, well, maybe more luminous galaxies, they are more probable of being the host of the GW source. And this is also motivated by the fact that, in general, more luminosity means also more mass. It also depends, actually, on which kind of band you're using, but okay. Let's say that, in general, this is like a good assumption. And it reflects the fact that if you have more mass, more luminous, so there is more probability that, in the end, that galaxy formed a binary of black holes because of the evolution of the stars and compact objects. So this is like the first term that you have to include, and which really accounts for the galaxies in your galaxy catalog. The second term is actually something that you have to add, again, as I was saying before, to account for the incompleteness of your galaxy catalog. And here there is another ingredient that comes into the game, which is the Schechter function. So the Schechter function is basically the number density of galaxy as a function of the absolute magnitude. It's a function which has been introduced, I think, by Paul Schechter in 1972 or something like that. And again, it's just a phenomenological function based on observations that gives you the number of galaxies as a function of their absolute magnitude. And this function depends on 3 parameters, which are called L star. Actually, yeah, it's the same. L star, alpha, and phi. Without going into details of this, but you just also have to include this function here. So you need to know at the moment we fix these parameters based, for example, on the distribution of the galaxy absolute magnitudes in the catalog that we use. For example, if I'm using Glade Plus here with a given band in the K-band is the observational band used to get the measurements of the redshifts, then I will have to choose parameters for the Schechter function which are fitted on observations which have been done in the K-band. Then you have another term here, which is, again, a dV over dz factor. And I'm doing this integral over 2 values here of absolute magnitude. This is like the threshold magnitude above which we are missing galaxies. For example, in each pixel, I will have I can compute actually the apparent magnitude threshold. Imagine that I have a sample of galaxies. For each of these galaxies, I have a measurement of the apparent magnitude, right? What we measure is the apparent magnitude. And then I can take the median of this distribution of apparent magnitudes, and then I can say, okay, I'm choosing conservatively this as my threshold value, meaning that all of the galaxies with a magnitude higher than the apparent magnitude, I'm missing them. Higher because the apparent magnitude, is the more negative, the more is stronger, right? The more is stronger the source. And so you have to do this. You have to integrate basically from the absolute magnitude threshold to the maximum absolute magnitude, which is like the highest, the faintest galaxies that we are missing. And there is also here a characteristic weight, again, to make things, to assign weights in the same way as we do also for the galaxies which fall into the galaxy catalog. Yes, I know that this is a bit complicated.
No, well, okay, but just to get
the picture,
an idea, I don't understand how the Schechter function, which is found based on observations, as you said, gives us information about something that we are missing.
Yeah, so because actually,
do you see?
I think I get your question. So the idea is that this should kind of be a universal function. So the idea is also that, in general, we assume like homogeneity and isotropy, but okay, mainly homogeneity, say, of the distribution of the galaxies. And generally, these parameters are fitted using samples of galaxies where we think like that we really are 100% complete. So you basically infer these parameters on a sample of galaxies where we know that actually we are not missing anything by some other methods, okay? And so in this way, we can say that actually the values of the Schechter function parameters can be used also in other, for other catalogs observed with the same band. So it's kind of, we kind of say that this should be kind of universal function. And this is, again, it's another assumption that we make, but in general, I mean, Schechter function is used in many contexts in astrophysics. So, okay. So, what is the main limitation?
There is another question.
Sorry.
And is this Schechter function mainly used to like fill in the gaps sky position-wise, or is it really to extend how deep we can go with these catalogs? Because I thought the main point was that most catalogs are not that deep in terms of redshift.
Yes. And this is indeed like the catalog that we used again, in the latest Cosmology paper by the LBK collaboration, which is GLADE Plus. As I told you before, this is like a compilation of 6 different surveys. Why? Because we want something which is all sky, because in general we have gravitational waves all over the sky, right? So we want something that we can actually use everywhere in the sky. But one of the main limitations of this catalog is that it is severely incomplete already at redshifts of, I don't know, 0.1 already, and yeah, 0.2 is basically kind of a 10% or 0%, 5% complete. Yeah, I mean, I will not go into the details of the different curves, but in general, this is like just to show you that they are this catalog is severely incomplete, and so we are not really getting much information from the galaxy catalog side, or if you want, from the first term here, using this catalog. And this is the reason why also I said that if you compare the posteriors of H0, dark siren versus spectral siren, I told you, well, the dark siren gives actually an improvement of roughly 9-10%. I mean, this is already something good because, I mean, given that we don't have a very complete galaxy catalog, I would say it's already an improvement. So, and by the way, I should also say that there are people inside the collaboration working on an improved version of this, which is called UpGlade, and which will be much better in terms of completeness. There could be other ways, maybe also to do this analysis, for example, using other galaxy surveys. For example, DS. DS has a very deep and very complete set of galaxies. DS is the dark energy survey made by the DCAM telescope in Chile. But the limitation of that is that it only covers 5,000 square degrees in the sky, mainly in the southern hemisphere. And so, in principle, it would be powerful only when used with the events, which kind of overlap in that same sky region. While this one, the idea of having something which is all sky, again, is in order to maximize the information that one can get by using all of the GW sources that we have. So, this is the new, what is the name? I think Grave, stellar mass Grave plot, something like that, that we have now. I think Chiara maybe showed this also, but here I'm like, so this plot shows basically the values of solar masses of the different objects that we observed so far. I ordered them by time. So you see, for example, in GWC1, we had 150914. You have 30 plus 35 solar mass black holes, which merged and which gave us something about 60, 63. And you have, the first, I think, 11, yes, including 170817, yes. And then you had GWC 2.1, which was including the O2 and the O3A, the first half of the third observing run, GWC 3, and now GWC 4. So we have a broader range here of masses. We also have very loud and very massive as well binaries. So we are improving. I will skip this. This is just the abstract of the cosmology paper which if you're interested, you can have a look at for all of the details about this. This is where we are now. So basically, we are here. Actually, no, I will show you, but O4b is what comes next in terms of LBK analysis and activities. And there will be something different. The fact that we will have Virgo, we had Virgo, sorry, because O4b ended. We had Virgo in the network. In O4a, we didn't, and we suffered a lot in terms of sky localization because we only had 2 detectors. But with Virgo, things actually improved a lot. As you can see here, I'm showing you some preliminary candidates. Okay, these are like GCN alerts that the LBK sends out whenever there is an interesting trigger detected by the low latency pipelines. And you can see, probably you can't because they are so small. I mean, there are like some events for which we have something like 14 square degrees in 90% credible region, 28 square degrees, 9 square degrees. I mean, these are incredibly small. And which are also, I mean, not super close by. It's not like 17017, which was at 40 megaparsec. But still, it's something 300, 360. So I think these events could be very interesting.
Can you give us an idea of about how many candidates are there in O4B of this kind? I mean,
so
not,
in O4B, 105.
I'm not assuming that all of them are that well localized.
No. I think here I took a sample of like 3, but there might be something like maybe 10, 15, more or less on these, with
okay.
10 maybe, okay, 10-ish, say. I don't want to be. But yeah, you can check it out also on GraceDB on the website here. You have a list of all of these sky maps with all of the alerts and things. So 10-ish, I would say, is probably fair.
How many of? Because I know, at least I think I heard that Virgo's sensitivity currently is still very low compared to the other two detectors. In the next observing runs, do we expect this rate of, I mean, to improve to the rate of events like this?
If I understand your question correctly, I think yes, in the sense. So here we used Virgo with its sensitivity, which was around 50 maybe, 50 megaparsec or something like that. But the BNS, I'm already referring to that figure of merit that we typically give. In O4C also, I think things are better. I am not showing here like other sky maps, but in principle, even if it is, even if it's not as much sensitive as the 2 LIGOs, in any case, it can help. It helps. I mean, you have seen it there, the sky map. So I think it would be, in any case, useful and interesting. Just because of the argument of the time delay and the triangulation, if you want. Even if Virgo data may not be super impactful in the parameter estimation, in the full parameter estimation of the GW source, including the masses, spins, and so on and so forth. For the sky localization, it's very useful in any case. So, and this is indeed O4C, which gave us something like, this is like updated to yesterday. So in total, like we have, and in O4C also there is Virgo. In total, we have something like 380 alerts, where I'm already including like the confirmed detections, 218. And we still have 1 month to go. So who knows, maybe tomorrow we have a BNS VDM counterpart. Could be. Okay, I think I still have 5-10 minutes. Fine. I don't want to abuse of your time. Let me go to Lisa, okay? So this is like a Lisa school. Yeah. Okay. So Lisa, right? So there is first a review I want to actually point you at, which is this one, done and made by the Lisa Cosmology Working Group. It's now published on Living Reviews Relativity 2023. You can also find the archive number here. So we have several sources here. Okay, so now we are moving to low frequencies, 10 to the minus 2, 10 to the minus 1, 10 to the minus 5. Okay, LIGO, Virgo are here. PTA is here. Here I will focus only on 2 sources which are deemed to be interesting for cosmology. So the first one, I have a few slides, so I mean, the first one is massive black hole binaries as bright sirens. So Alberto yesterday told you and convinced you, I hope, that these systems might have an electromagnetic counterpart. These are the ones that you see here. So again, you have already seen this plot, I think, many times. But you have the strain amplitude versus the frequency. So how can we use these systems actually as bright sirens? So here I'm giving you an example. And actually, it's funny because Alberto worked on this model, so I have to present like his results. I think he could have better done the job here. But so there have been some studies starting from 2016 and so on, looking at the possibility of actually using LISA sources as standard sirens. And in the case of massive black hole binaries, for example, there will be, I mean, probably up to 100 detections maybe per year, up to very high redshift, but not all of those, up to, I said, no, I didn't say 100. But probably only a few of those will have an electromagnetic counterpart, as Alberto was telling you yesterday. And so recent studies, here I'm just giving you, the results. Recent studies suggest that we might have from order 1 to 5 bright sirens per year, potentially up to redshift 7. And the way in which the EM counterparts can be detected are, I'm not going through the sources, through the mechanisms that produce this because Alberto covered them. But basically the way we can detect the EM counterparts are, for example, either by observing the EM counterpart in the optical with Vera Rubin, and this is what LSST or Vera Rubin Observatory, and this is what they did in this work, Alberto and collaborators in 2022. Or, for example, we could first look and detect the radio emission, for example, with SKA, or we could look at the X-ray emission, and this is what I'm showing you here with Athena, for example. This can then be used to improve the sky location of the source and eventually get the redshift with the extremely large telescope, which is like a spectroscopic facility. And this is just one example. So in this paper, they consider different scenarios by which you can observe the EM counterpart. The final result, after considering, for example, more complications due to the fact that that might be that you cannot always observe the emission of the EM counterpart based also on the jet and so on, gives us this roughly number. This rough number, which translates into constraints on h, this is little h, is just h naught divided by 100 if you want, and omega matter. And in this work, they consider several simulations, several realizations for the massive black hole binaries with the EM counterpart. And this corner plot, for example, shows, like, say, the best scenario, a median case scenario, and the worst case scenario. And you see that, so this is like a usual and common degeneracy between h naught and omega matter. Again, this is due to the luminosity distance redshift relation. But you can see that how the correlation actually evolves and actually shrinks as we are in, worst case or best case. What does it mean, worst and best? So, for example, you may have, in the worst case scenario, maybe a lower number of sources. For example, in 4 years, I think these are for 4 years of observation. It could go down to, I don't know, a few, 20, 18, something like that. Or the best case where you may have more, 30, 40 potentially. So there is some variability. But, I mean, this is, again, to show that in principle, this is a very interesting problem. Now, I will show you this later in another plot that I'm going to show you now. But these sources will be observed at redshifts which in principle are kind of not very easy to observe, at least not with LVK. Maybe with the Einstein telescope, we'll see. But I mean that, we are going to really probe the high redshift range. And so we are really probing the cosmic expansion history, not just H naught. We will also get information about omega matter. Extreme acceleration spirals. Extreme acceleration spirals are the second source which we think would be very interesting to be used as dark sirens. Why dark? Because we don't expect really an MRI to have an electromagnetic counterpart, although I have seen, like in the literature, even recently, several astrophysical models which could predict actually also EM counterparts for these systems. But basically, here the idea is that these systems are going to be in LISA band for a long time. We're going to observe tens of thousands of cycles of orbit. This, in practice, means that we will have a very good sky localization of these events. And in a study that we did like in a few years ago, we showed that, in principle, if you combine these events with a galaxy catalog, a simulated galaxy catalog we used here, you can get constraints on H0 and on omega matter as well. And these are kind of interesting because, so for example, this is like the luminosity distance redshift relation, where I am fitting the best fit cosmology that we obtained, with some error bars, of course. Each of these little blobs, which you probably cannot see, are each single EMRI, okay, in the L redshift uncertainty. And each of these points here, color points here, represent galaxies associated to each of these EMRIs, which I'm putting here on the same DL just for visual representation. But what this shows basically is that you see the redshift range that in principle could be covered by these EMRIs. I think Richard probably showed you and mentioned you Babak et al. 2017, which is the paper which typically made produce EMRI catalogs, and which is probably still the most up-to-date paper showing the parameter estimation of EMRIs and so on and so forth. There were 12 models they considered in that paper, which were labeled M1, M2, M3, M12. And these are like, in this study we consider like a fiducial model, which is M1, a pessimistic model, which is called M5, and an optimistic model, which is called M6, where here the degree of optimism reflects the number of sources that eventually each of these models predict. And so you can see that, for example, using even two only EMRIs in one of these scenarios, you can already get something which is on the order of 6-7%. And in the most optimistic case, we found that in principle, H0 could be at the level of 1% and so on. And how many of these sources? Well, again, this was obtained in the scenarios of 4 years of observations or 10 years of observations. So again, you can see that there is some variance in the number of events because, again, EMRIs, we don't really know how many we will observe. Could be 1, it could be 1,000. But 1 for sure. Okay. Last slide is this. So this is something I've been showing for some time. I hope that soon it will be kind of finalized. So this shows like the idea behind combining different sources. For example, here we have the EMRIs and the massive black hole binaries. And why do we want to combine them? Because there is a different degeneracy in the cosmological parameter space here. You see that, for example, EMRIs are more sensitive to H, and massive black hole binaries are more sensitive to omega matter. And so once you combine these two together, you get something which is like the black posterior here. And so this improves your measurement. Why do we have like the EMRIs are more informative on H? Well, if you look at this plot here, which is always the luminosity distance redshift relation, EMRIs happen at lower redshift in general. Another caveat I should say is that in the study that we did, which are also the results that I'm using to make this plot, we only went up to redshift 1 because there we had a galaxy catalog which had galaxies only up to redshift 1. So in principle, this could even go further, although in that case, I guess that EMRIs are not very well localized. But the point is that EMRIs and massive black hole binaries, at least with breath sirens, they do cover different regions in the parameter space. And so EMRIs are more sensitive to H0, while massive black hole binaries are more sensitive to omega matter because we're at higher redshifts. There are also other differences here. For example, there are massive black hole binaries which are better measured and which have better measurements of Z. For example, you see these are very tiny, very strict regions. Here I'm just using the uncertainties obtained in Alberto's work. Why? Because some of these redshifts are obtained with Vera Rubin and they're photometric. Others are obtained with the extremely large telescope and they're spectroscopic. And you can already see like why I was saying that there's a difference between using spectroscopic and photometric redshifts. But okay, so this is like the general idea. And again, We expect potentially to get something on the order of these figures here, 68% level. So an H naught which might go maybe down to sub% precision, and omega matter which could potentially also give us interesting constraints, although maybe not super competitive as compared to other EM probes. But still, these are, again, other measurements which will complement the EM measurements that suffer from different systematics. So again, I'm not saying that, I'm not selling this as, oh, GWs and LISA sources will solve our problems in cosmology. But again, these are measurements obtained with different methods which suffer from different systematics. And so this can help us, for example, in discerning a better understanding the measurements we got so far. Okay, I think I will stop here. Yeah, thank you.
Thank you very much, Danny. Are there questions? Yes, there is one. Okay.
Okay, so I have two actually. The first one is I remember that in O4C, the event detection rate was kind of lower than the rest. I think we could see it on the plot that you had. Yes. No, O4C.
Sorry? This?
Yes.
Yeah, sorry.
Can you remind me why?
So I should check this. I think that Virgo had some issues at the detector level. I'm not sure whether it was due to the calibration. I might be wrong. But if I remember correctly, the lowest sensitivity was due to some problems that Virgo was suffering during O4C.
Okay.
But, yeah.
And so my second question is on MRIs.
Yeah.
So you said we don't really expect them to be bright sirens. Isn't there like any scenario where the secondary compact object would be a neutron star and we would see a tidal disruption event?
Oh. Yeah, but TDEs are probably not really tidal disruption events. Are not really. As far as I know, so these are different things, right? Because an MRI, in principle, is defined as something which, at least in the models we have been considering here, has it's a compact object. It's a compact object. TDE are different, and I think the emission of the gravitational wave signals might not be kind of detectable with LISA. Maybe, but according to, some people who are working on TDEs, maybe there is some of you here. Yeah, okay.
There's a theory that these things called quasi-periodic eruptions are like a TDE and an MRI together.
Yeah.
And then you could maybe get an EM signal from an MRI, but it's just a theory right now.
But that would produce an EM signal in theory?
Yeah.
Okay.
Okay, so in principle, yes, but yeah, so far the astrophysical models of MRIs here, they've been considering only compact objects. Maybe Natalia wants to add something?
Yeah, that's so what I was talking about is kind of like you get a tidal disruption event, and then there's a disk, and then the compact object goes through the disk, and then that's what produces an EM counterpart.
Yeah, okay.
Yeah.
But usually this ones you would see.
Yeah, true.
I think usually the electromagnetic ones you would see before you would start observing the MRI in the gravitational wave band. So they might not coincide, at the same time in the electromagnetic and gravitational wave.
Yeah, so, that's a good point.
Other questions? Yes.
Are there people, you mentioned all of this hierarchical Bayesian inference thing. Are there studies that are trying to do this via simulation-based inference?
Yes.
And would that be useful in this case, or is it an overkill?
I think it could be useful. So, for example, I have in mind, I think, Laghi et al. 2024, if I'm not wrong. I think they are using these kind of methods here. However, yeah, I'm not sure whether at this moment we are already kind of ready to use these models. I don't know if it could be an overkill in the sense maybe the computational cost of this is that I guess you need to have simulations, a lot of them, also in order to train your models. I don't know how much that would perform as compared to the usual analysis that we do here. But I think, yes, there are people who are working on that, and there are also some papers. So I didn't mention this. I didn't mention a lot of things, actually. Sorry. But I didn't mention that there are other methods. There are neutron stars by measuring the tidal deformability, other methods to get cosmological parameters. Here I only wanted to focus on a couple of them because these are the ones that have been used typically. I didn't mention about the complications in the computation of that integral in the hierarchical likelihood. So all of these, I mean, in any case, I think I put some references here. So if you want to get more about this, you should be able to find them.
Can I ask one small thing?
Yeah.
Can you give us an idea of how much it took to you to get those posteriors given all of the data by O4A?
Okay, so I have to say that...
what is the computational...
I didn't...
Not, yeah, okay.
No, okay. So I was the chair of the paper writing team of this paper.
Okay.
I was coordinating like the paper writing team and also, I mean, the group of analysts who really produced the paper, so the plot, actually. So it wasn't me who did this. But we did it, okay? So we started working on this probably beginning of last year, I think. In general, there is the policy, I don't have the plot here, there is the policy that data should go public like 18 months after the end of the observing run, 18 months, I think. And so, I mean, O4B ended like in, I'm not sure if I wrote it here, no. But yeah, it ended like in 2023, beginning of 24. And so basically, as soon as the observations end, then there is the internal analysis. You have to make the parameter estimation of the GW sources, offline parameter estimation. This requires time. There are several iterations in the process. In the end, when you get the final parameter, the final catalog, if you want, then you start, at least in our case, we are a kind of analysis that we have to wait for that previous step to happen. So you have first to make the parameter estimation, then everyone's, even the TGR paper, like the paper who presents test of general relativity, they have to wait for the catalog to be ready. The rates and population paper, the paper which describes the study of the population properties in more detail, and so on, they also have to wait for the catalog to be ready. And so we have to wait for this to happen. And this happens somewhere, on the order of months several months after the end of the observing run. And then once you have this, then we can start working on this. But there are several steps and things that one has to do here. I mean, I will not go into details, but more or less I would say maybe a couple of years, something like that, a bit less. It's a collaboration paper, so I mean here like you have to, it's a bit different as compared to LISA consortium because, again, LISA doesn't have data yet.
I think we need to close here, so maybe you can ask questions to Danny. So let's applaud again.